In this word problem, we're given an equation that we need to differentiate implicitly. So let's read the problem. The number of X compact refrigerators that people are willing to buy per week at a price of P dollars is given by this price demand equation. And we're told that P is a function of X. So the first part of the question, part A, is asking us, what does that notation mean? This P equals P of X. What is that telling us? Well, algebraically, it's telling us that price, it's letter P, is a function of the number of refrigerators demanded, so letter X. But the calculus that I should read from this is telling me that X is acting like an input variable. So anytime I take the derivative of X, the derivative of plain old variable is just going to be 1. And P is a function. So since P is a function, when I take the derivative of P, it's not going to be a 1. I'm just going to record that as P prime. Okay, so B is asking us to use implicit differentiation to find dp over dx. Okay, so first of all, what is implicit differentiation? Implicit differentiation means you need to find the derivative as is, as the equation is written. Don't do any algebra to rearrange the equation before you take the derivative. You just take the derivative starting the way it's written. Now, what does this dp dx notation mean here? What is this telling us? Okay, so dp over dx, what is that asking us to do? Now remember, derivative is a rate of change. It's the change in the outputs over the change in the inputs. Okay, so when I had that notation where p was a function of x, I can see x is the input. All dp over dx is asking us to do is it's another way to say find p prime. Find the change in the output with respect to the change in that input there. So we're just finding p prime. So basically, dp over dx is just another way to write p prime. Okay, so that means for part B, I'm going to write the equation exactly as it was given to me, and I'm going to differentiate exactly as it was written. So I'm going to take the derivative of the left-hand side and the derivative of the right-hand side. But I also know that I don't have any derivative rules that involve a square root. So I'm going to need to rewrite that square root. Okay, so before I take the derivative of any of this, I'm just going to go ahead and rewrite my equation to have a fractional exponent. So I'm going to rewrite that as x equals 900 minus 30, then p plus 25 in parentheses to the 1/2 power. So no calculus has happened here. This was just algebra. Now I know I can use my power rule with chain rule. So now I'll take the derivative of both sides of this equation. Okay, so when I take the derivative of x, it's just x prime. But since x is acting like a variable, we know that x prime is equal to 1. So that's really just going to be 1. Okay, and then I'm going to take the derivative of 900. Well, 900 is just a constant. So when I take the derivative of a constant, that's going to be 0. But I don't really need to write that. I am in this case because I want to distinguish what's happening here with this subtraction. So I'm going to write the 0 there, but it's not necessary. And then I need to do my power rule with chain rule to find the derivative of this last piece, because I can see that my p is in the base, and the base has a constant exponent, so that just means it's set up for chain rule. And since my base is not a plain variable, the base is a binomial, it's a linear function here, I'm going to have to do my chain rule. So let's go ahead and do our chain rule here, our power rule with chain rule. I drop my exponent down to the front, so 1/2 times 30 is going to be 15, but I'm subtracting that amount, so I'm going to write minus 15. Then I rewrite my base exactly like it's given to me. Then I decrease that exponent by 1, so that brings my exponent to negative 1/2. Then I need to tack on the derivative of the base, and that's where we have to be a little bit careful, because this p, this letter p right here, is acting like a function. So when I take the derivative of p, I'm going to get a p prime in there. that's not equal to 1. So let's just look at this space. This space is set up kind of like a linear function here. So we have a constant. We know the derivative of that constant is going to be 0. Okay, so when I take the derivative of this p plus 25, that 25 is going to go to 0. But what is this p? Well, you might just see, okay, well, the derivative of p is p prime. Just p prime, because p is a function. Or if you really want to, you can do the whole chain rule. So let's do the whole chain rule, power rule with chain rule here. So there's an understood exponent of 1. I would drop that 1 down. I would rewrite the base p. I would decrease that exponent by 1, and then I would tack on the derivative of the base. But p to the 0 power is just 1. P prime is not 1, so I get 1 times p prime. All that's just going to be p prime. So when I have p plus 25 and I take the derivative, and that letter p is acting like a function, the derivative is just p prime. So what does that look like? Let's clean it up. We have a 1 equals, I'm not going to write that 0, but I still have a negative 15 base to the negative 1/2 power, and the derivative of the base was just p prime. And all we're being asked to do here is find dp over dx, which was another way to write p prime. So all I have to do is isolate this p prime, get it alone. And right now, p prime is currently being multiplied by negative 15 and the binomial to the negative 1/2 power. So I'm just going to divide that on the other side. And then you can stop right there. You don't have to do any algebra to clean this up. We weren't asked to, do anything extra there. So I'm going to write p prime as 1 over negative 15 p plus 25 to the negative 1/2 power. Now, of course, you can do some cleanup here if you want to. If you want to relocate the base to the numerator because it's attached to a negative exponent, if you want to relocate that, you can. So that would give me 1 over negative 15, and then I would relocate my binomial. And when I do that, the exponent turns positive. I could do that. I can keep cleaning it up because I don't need that understood 1 there. I could also pull this negative either to the numerator or out in front of my fraction. So the most simplified version would probably look like this. That's kind of messy, but you could just stop here as soon as you isolate your p prime and you're done.